When you resize a photo on your phone, the image doesn't distort because the proportions stay locked. In geometry, this relationship is called similarity. It describes shapes that are identical in form, even if they occupy a different amount of space. There is a strict distinction between shapes that are congruent and shapes that are similar. Congruent shapes are a direct copy-paste, identical size and identical shape. Similar shapes follow the pinch-to-zoom rule. The shape is preserved, but the scale has changed. We represent this relationship using the tilde symbol. For two triangles to be mathematically similar, they must satisfy two conditions. First, all corresponding internal angles must be exactly equal. Second, every corresponding side must scale by the same uniform multiplier. The angles act as a rigid skeleton that defines the shape, while the side ratios determine its physical scale in space. Because every triangle's internal angles must sum to 180 degrees, knowing just two angles match means the third is mathematically forced to match as well. This geometric certainty allows us to use criteria like AA, SSS, and SAS to guarantee similarity without needing to measure every individual side and angle. However, SAS contains a trap. Simply having two proportional sides and one equal angle is insufficient if they aren't in the right order. This specific configuration fails the similarity test. To satisfy the SAS criterion, the angle must be included, meaning it is sandwiched directly between the two proportional sides that form it. These geometric rules are rigid. Applying a shortcut like SAS to the wrong set of parts results in a mathematically invalid proof. Identifying similar triangles is only half the battle. You also have to name them correctly. When a triangle is rotated or flipped, you cannot rely on its visual orientation. You must match the vertices based strictly on their corresponding angles. Let's try it. Pause the video here. Use the color-coded angles to determine the exact name for the second triangle that corresponds to triangle ABC. If you matched green to green, yellow to yellow, and pink to pink, you got triangle PQR. This specific order is vital because it dictates which sides are proportional to one another. You can extract your side equations directly from the letter order. The first two letters, AB over PQ, form your first fraction. The last two, BC over QR, form the second. And the first and last, AC over PR, form the third. The similarity statement translates the visual drawing into a mathematical framework. When vertices are positioned in the correct sequence, the letters generate the proportional fractions required to solve the problem. Let's solve a bow tie problem with two triangles, parallel lines, known lengths, and missing x. 1. Prove similarity. Vertically opposite and alternate interior angles satisfy the AA criterion. 2. Write the statement by aligning vertices. 3. Extract fractions, plug in lengths, and cross-multiply. Even complex geometric figures are built from simple triangles. Once you identify the angle rules, the underlying similarity becomes clear. Solve any similarity problem with this three-step process. Prove the criteria, match the vertices for the naming statement, and extract the fractions to solve. Screenshot this checklist for your next study session. By following the rigid rules of geometric correspondence, you can convert a visual puzzle into a predictable algebraic equation.